Let's do some fun stuff for the rest of class today, starting with some interesting animations to illustrate these ideas. Let's go ahead and once again do f of x equals e to the x. I guess I had that up there already. And let's go ahead and enter the general formula for the nth degree Taylor polynomial. So those have been re-entered now and updated. Manipulate can make animations of anything in Mathematica. And I do mean really literally anything that can be parameterized, including graphs. We can plot f of x and p sub n of x. Pick an interval, -5 to 5. It probably will be a good idea to fix a plot range in both the horizontal direction and vertical direction, because especially in the vertical direction, Mathematica makes adjustments if you don't fix it. So for the x direction, I'll go -5 to 5. And for the y direction, something bigger, maybe -20 to 20. Outside the plot, put a comma, and then put your animation parameter. What is it varying over? It's n, starting at 1, maybe going up to 20 or so. If you leave it like this, it does continuous increments, which doesn't make sense in this example because the summation n is a discrete value. You can make it jump up by 1 each time by adding an extra comma 1. So what are we about to see? We're about to see the Taylor polynomials approximating e to the x as n gets bigger and bigger. E to the x will be red, the approximation will be blue. So there is what you see when n is 1. E to the x in red, and this blue graph, think about it, that's the graph of 1 plus x. Slope of 1, y-intercept of 1. Let n increase to 2. You're going to get a quadratic parabola approximation to e to the x, which approximates e to the x really well near 0. The function values are the same there, 1. Slopes are the same there, 1. Second derivatives are the same there, 1. Let n increase to 3, you get a cubic approximation. Let n increase to 4, you get a 4th degree. And as n increases, the approximation gets better and better, not just near 0, but over the entire number line. And it's like a dog wagging its tail. We could go out further, maybe -10 to 10. And maybe let's do -50 to +50 here. The dog is wagging its tail, giving you better and better approximations over bigger and bigger intervals as n gets larger and larger. Never do these always equal. But in the limit, as n goes to infinity, no matter what x is, the resulting series does converge to the function. They are equal. Let's do something similar for the cosine function. First, reminder, what is the series for cosine? Series cosine. It thinks x is 8. Clear x. It's all even powers, actually. If we look at the pattern there, notice the signs alternate, plus, minus, plus, minus, plus, minus. A -1 to the k will take care of the alternating signs, starting with the positive when k is 0. -1 to the 0 is +1. The powers of x, though, are all even. I need to have 2k up here instead of k, because in the summation, k is 0, then 1, then 2, then 3, etc. But I want the powers of x to be 0, then 2, then 4, then 6, then 8, etc. Also the same kind of thing with the factorials. And let's animate that. I will want a smaller plot range in the vertical direction. Let's see what this one looks like. Are you ready? Flap your wings. Something years ago, I showed this in a Calc 2 class. 6 months later, somebody from the class came by my office and said, Dr. Kinney, you changed my life. In particular, that animation changed my life. I decided to go more deeply into math because of it. So it changed my life. It's amazing. The approximation gets better and better as n gets larger and larger. In the limit, as n goes to infinity, it's perfect. They're exactly equal. What about when n, with sine? The series for sine involves all odd powers. There it is. For the formulas, change the cosine to a sine, change the even powers to odd powers. Add 1 in here and down there for the factorial. Sine's an odd function, so we're not going to see the exact same thing here. It's like a bird flapping its wings, but it's kind of like a sideways bird. These seem to confirm it converges for all x. But wait a minute, we have examples that don't converge for all x. What's our favorite one of those? Yeah, geometric series. Like that is what I was thinking of. That only converges between -1 and 1. What happens with the animation in that case? The formula for the summation is simple. Trying to approximate the red graph with blue graphs. That vertical line is not part of the graph. It's a vertical asymptote. Ignore it. It seems to only be working between -1 and 1. Intuitively, it is kind of because the red graph has a vertical asymptote at +1. That's why it doesn't work at +1 or bigger, I guess. But what about, why doesn't it work when x is less than -1? It's not so clear. But true.